Well, here is the official power rule with a constant multiple. So f of x is equal to a times x to the n, where a and n are constants. Then, well, here's the derivative. And we've done this, but now we're formalizing it with some variables. We would take the coefficient and multiply by the exponent. And then we would take our variable and subtract 1 from the exponent. There you go. So let's go through a few examples on the back. And we're going to have to rewrite some things. So I'm going to grab a different color pen for the rewrites. And then we'll start figuring out what the derivatives are. And the purpose of these next 4 problems, number 1, 2, 3, and 4, are so we can see the different ways that we would have a problem worded that is asking really for a derivative or the value of a derivative at a specific point. In other words, asking for the slope at a point, or the slope of the line tangent to a point, or the instantaneous rate of change. It's all asking for the same thing, just with different contexts. Okay, there we go. A little more light here. Let's rewrite this one. So f is really equal to, for our purposes, here's a square root, so 6x to the 1/2 plus 8x to the -1 and then minus 2. That's fantastic. Now we're going to find the derivative of that. I'll turn that down one. There we go. We're going to find the derivative of that and then evaluate it at 4. So the derivative of x would be 6 times 1/2. 1/2 minus 1. 8 times -1. -1 minus 1. And then technically 2 times 0, -2 times 0, because this like x to the 0 here. So we don't even need to worry about it. So it's gone. And you can rewrite this if you like. I think it's going to be beneficial if we do. So let's write it the way it should be. This negative exponent and this negative exponent will move both of those x's to the denominator. So we'll have 3 over x to the 1/2. Well, a variable that is anything raised to the 1/2 power is a square root. So 3 over the square root of x minus 8 over x squared. We have now found the derivative. We have not evaluated the derivative at 4. So we would like to know what the value of the derivative is at a specific value, at a specific point. And we will do that by plugging in a 4. F prime of 4 is going to give me 3 over the square root of 4 minus 8 over 4 squared. Okay, well that's 3 over 2 minus, let's see, that would be 8 over 16. That's 1/2. So 3 halves minus 1/2 is 2 halves, and that would equal 1. Okay, so given a function, find the value of the derivative at a point. Or, what's the slope of the line tangent to that graph at that point? It's the same question. Same question. So let's switch colors just for fun. For variety. It's not just fun, it's also variety. Getting used to different notations and different ways these things could be asked. There's not a rewrite necessary here. This is a polynomial in its most pure sense. It looks like a polynomial. It is a polynomial. It smells like a polynomial. It tastes like a polynomial. 1/4 times x, 1/4 times 2 is 1/2. Subtract 1 from the exponent. 3 times 1 is 3, and subtract 1 from that exponent. So we have the derivative. Now we're just going to plug in a -2, so 1/2 times -2 and then plus 3. That's going to give me -1 plus 3, which gives me 2. There we go. That one was pretty straightforward. So the next one, given y equals 5 over x, evaluate dy over dx when x equals 3. Here's a different notation. Same question, different notation. Okay, so this is the Newton notation, f prime. This is the Leibniz notation. They both have their own practical aspects, which is why we keep them both around. Let's switch colors again. Let's go green. Well, actually, let's write this rewrite first. So this needs a good rewriting. Y equals, not F, y equals 5x to the -1. So that's the original function rewritten. And now we're going to find the derivative. You could call it y apostrophe, y prime, if you wanted to. I am going to call it dy over dx. That's where I'm switching to purple. So the derivative, the change in y divided by the change in x, that's slope, essentially. It's the same idea. -5x to the -2. And let's fix this a little bit so it looks just a little neater. -5 over x squared. There we go. We don't always have to rewrite it, but when we're evaluating it, it probably comes in handy to have it in a format that we're used to seeing it. So we are going to evaluate this at x equals 3. And here's a relatively new notation. I don't think you've seen this one before. But if I want to evaluate something at a specific value, I can put a vertical line, and then at the end of that vertical line, at the bottom of that vertical line, talk about what I'm going to evaluate. Okay, let me clarify. What I really want to do is evaluate dy dx, dy over dx. It is often called dy dx, even though it's dy over dx. I want to evaluate that at x equals 3. So dy over dx evaluated at x equals 3. And that whole thing would equal, well, negative 5 over 3 squared, which is negative 5 over 9. So here's a different notation. So y I've figured out the derivative. It's referred to as dy over dx, also y prime. That'd be fine. And evaluating it at x equals 3 can look like this. Number 4, find the instantaneous rate of change. Same thing. I want to know the slope at a point. I want to know the change at one point. And we'll put this one in red, like I'm shouting at you or something, I guess. I don't know. So let's see. F prime is equal to 16x. This is going to be really straightforward, right? So I want to know what happens at x equals 1 with the slope. So the slope at 1 is 16 times 1. Nobody's surprised at that. That would just be 16.